Hey, Is. I got a new webcam. Can you tell? I think I'm a little less washed out, I hope. Maybe a little warmer. Okay, so today what I wanted to do was kind of sit back, relax a little bit. You know, it's midterm week, everybody's stressed out. So this lecture, I wanted to just kind of be more reflective, a little bit more of a review type lecture. So, and this will hopefully track better with your DLs than just charging forward. So, what I'm going to do this time around is I'm just going to go through a few two-dimensional examples using momentum and force, and discussing like how to approach these kinds of problems, how to take a look at them and say, okay, this is the variable that I'm interested in. I should subdivide my universe into like system and environment in this way. So, yeah, okay, let's hop into it. All right. So the first example I wanted to talk about is just a ball that has been thrown. So I'm not going to worry too much about how the ball acquired its initial momentum. I'm just going to say it is a ball that has been thrown. So, oops, I start out with this ball. Here we go. I'm going to make it a red ball. Start out with this ball. And this ball is thrown, it has been thrown rather, up at some angle. So I'm gonna mark my vector here for its velocity. Let's say that its initial velocity, vi, let's say that it's, I don't know, let's call it 25 meters per second. Sounds good. And I'm going to go ahead and say that the angle relative to the vertical is, eyeballing that, let's call it 30 degrees. 30 degrees. Should make life simple. Okay, so what I've given you here is a representation of the velocity in terms of the magnitude and direction, right? So I don't have the velocity in a vector form just yet. I have the magnitude and direction. Let's also say, just for funsies, that the ball is 2 kilograms. 2 kilograms. All right. So I have a couple of questions. Let's set it up like it's a real problem. So I have a couple of questions. One, how does the ball's momentum change due to the interaction with gravity? I suppose to answer that question, I'll need a couple of other things. So I'll need part one. What is the initial momentum vector P? I'll call it Pi. And then, of course, if I'm talking about a change, I'll also need some final. 2. What is the final momentum vector P? Okay, so I realize now I need to specify 2 more things. So the first thing I need to specify, and this is just like me setting up the problem still, this is not something that you're supposed to know. The first thing I'll specify is that I'm just going to say that my final frame, so T final, I'm just going to say it's 2 seconds after my initial window here. So I'll say T initial is 0 seconds. All right, the very last thing you need to know to solve this problem is that the force of gravity acts down. Cool. And on this ball, the force of gravity is going to be 20 newtons. All right. So this comes from the fact that the ball is 2 kilograms, and the force of gravity is just the mass of the ball times g. That's how big the force due to gravity is. And I don't think this is, I want to say this might have been touched in 7a, but not properly stressed. So there it is. Force of gravity is mass times gravity. The mass of the ball, the mass of the object, times g, the acceleration due to gravity. Okay. So my questions are all about changes in momentum. So the ball's momentum's change, the change in the ball's momentum is the same as j, the impulse. So j is just delta p. And delta p is the same as force, net force on a system, times delta t. And delta p here should be a vector. There we go. Okay. So let's go about looking at now this part one. So in order to find the change in momentum, I'm going to need to find the initial and final momenta. So in 2D, the way that I think about vectors is I need my two components. So I need the x component and the y component. So let's find the x component. So first of all, I can find the x component of momentum either as mass times velocity in the x direction, or I can calculate like the whole vector p, capital P, and then take the x component of that. Since I'm lazy, and that requires one extra step of like multiplying, anyway, it doesn't matter too much. Since I'm lazy, I'm just going to do this method. The x component is just the mass times the x component of velocity. So what's the x component of velocity? The x component of velocity here is just the magnitude of v times the sine of the angle. Okay, now if you're looking at the last video, or if you went over trig in your DLs, you might be scratching your head for a minute because this is the x component. And usually when I think about the x component of something, I say it's, you know, the magnitude of the vector times the cosine of the angle. So why would this be sine here? One important thing you should always look at when doing these kinds of problems, or problems generally, is whether your angle is being measured from the vertical axis or from the horizontal axis. So if you go back to like SOHCAHTOA, if you go back to the trig SOHCAHTOA rule, I've got the hypotenuse, and if I'm looking for the x direction, I'm actually looking for the opposite, the O. So that's so. Sine of the angle is going to be the opposite, the x component, over the hypotenuse. So when I'm using the vertical axis to measure my angle from, I'm actually going to use sine of theta for the x component. Okay, let's do that. So do I remember my unit circle or not? So this is going to be 2 times 25 times sine of 30. And sine of 30 degrees, I think is 1/2. Let's double check myself though. So I think this is just going to be 25 here. Double check. Yeah, it's half. We're good. All right, sig. So I just, 2 cancels with a half, so I end up with 25 kilogram meters per second. All right, that's the x component of momentum. Similarly, I can find the y component of momentum. So for the y component of momentum, I have two choices. I can either know that the magnitude of momentum, the total thing, is just m times the magnitude of v. That's 2 times 25, which is 50 kilogram meters per second. And then use this knowledge and the knowledge that the two components must sum up like this, px squared plus py squared. They have to sum up to the total, and I square root it. Sorry about that, close one. So they sum squared like you would just a distance, right? A squared plus b squared equals c squared. I can use that, or I can use the same rule that I used above, except for with cosine instead. So py is going to be mvy, which is m times magnitude of v times cosine of theta. Again, they've swapped. They're usually sine of theta for the vertical component and cosine for the x component. But here I'm measuring my angle relative to the vertical instead of the horizontal. Okay, and what I get out is, what is this one? It's going to be like root 3 over 2. Isn't that what it is? Hang on. So it's going to be 2 times 25 times cosine of 30. And cosine of 30 is 0.866, which is root 3 over 2. So this is 25 times root 3, which is approximately 43.3 kilogram meters per second. So to answer my initial question, this part 1 here, what's the initial momentum vector, pi? I look and I say, okay, px is 25, so p equals 25, comma, the y component is going to be 43.3, and that's kilogram meters per second. Okay, now I mentioned this other method over here. So since there's two ways to get at the same answer, I can verify that this method gives me the same result. So what I want is for px and py, when I square each of those and then add them up and square root them, I should get out 50. So let's double check and make sure that's true. So double check, gut check here. Is 25 squared plus 43.3 squared square rooted, is that 50? And if I run the math, I get 49.99999, which is close enough because it's physics. All right. So so this should be right. This is my initial momentum vector. Sick. Now, what is my final momentum vector? PF. Now I have to think a little bit more about my system. So we're going to address number 2 here. What is the final momentum vector? Okay, so if I want to look at my final momentum vector, I need to think about how I get there. So the final momentum vector is defined as the initial plus the change. Okay, and what is this J? What is that J? J represents a net force. It represents an exposure to a net external force outside of my system. So what I'm doing in this problem is I'm implicitly assuming that the ball is my system. I'll draw a little box around it. The ball is my system. And I have to think about whether there are any external objects, any external entities that are interacting with this ball. So in this case, there is an external entity. It's just gravity. So gravity represents a force that is not like between parts of the ball or like, it's not internal to the ball. It's external to the ball. It's not the how do you say this? It's not like the atoms of the ball pushing against one another. It's gravity from the outside, from the Earth, pulling on the ball. So there is a net external force. That tells me that the initial and final momenta aren't going to be the same. In other words, even though total momentum of the universe is conserved, momentum here is not going to be conserved in the sense that for my small part of the universe, the momentum is not going to be the same. We've got a net external force, so we're allowed to have variations in momentum. Okay, now, to find my final momentum, what I'll need to do is I'll need to add my initial momentum, which is 25 or 43.3 kilogram meters per second, plus my change in momentum. So what's my change in momentum? Well, the change in momentum, J, the change in momentum, is just F net times delta P. Or not delta P, sorry, delta T. F net times time. So the longer my force acts, the greater the change in momentum. So in the problem statement I just gave, that the net force due to gravity on this ball is going to be 20 newtons. And the delta T is just going to be 2 seconds. But wait, look at this. So I've got a vector quantity here, and I've got a scalar quantity here. So that can't be right. I can't add a scalar to a vector. I can multiply a vector by a scalar, but I can't add a scalar to a vector. That just doesn't make sense. So what I need to do is I need to figure out the direction of J. Okay, so the direction of J. How is J changing? How is my momentum changing? In what direction is the force acting, is another way to say that. Well, I see here that my force is acting down. So if my force is acting down, I can draw in, if you like, my coordinate axes. Here's X, here's Y. Okay, well, if I look at this now, it looks like mg, this force due to gravity, is pointing down on the Y direction, and it doesn't have any component in the X direction. It's not pointing left or right at all. So if I wanted to write out J is going to be F net, that's going to be 0, mg, negative mg, it's pointing downward. G is a positive number, m is a positive number, but I need the overall vector to be pointing down. Negative mg, because it's pointing down, times 2. Okay, now I'm feeling a little bit better. When I multiply that out to get my J, I get 0, m is 2 kilograms, G is 10, and 2 for delta T, 2 seconds. All right, and my result is 0, 40 kilogram meters per second. All right, sweet. So now I'm ready. I can finally find my final momentum by adding up the initial momentum to the net impulse. So 0, 40 kilogram meters per second. This tells me that the negative 40. Sorry about that. Okay, so I made a typo. There should be a negative up here. So it was negative mg times 2, negative 2 times 10 times 2, negative 40, negative 40. Okay, sign error. So I add up my vectors. How do I add vectors? I add them up component-wise. So the final momentum is going to be 25 plus 0, comma, 43.3 plus negative 40. All right, and what I get out at the end is 25, comma, 3.3 kilogram meters per second. All right, so let's dial back for a minute. So first of all, let me label my result. The final momentum was 25, comma, 3.3 kilogram meters per second. First thing to note, momentum was not conserved. So the final momentum is not the same as the initial momentum. Why is this possible? Because I've got a net external force acting on my system. It's an open system in that sense. It's got this gravitational force acting on it from the outside. The change in momentum I found along the way by applying force times change in time. That gets me my impulse, which is the same as change in momentum. Here's that. Okay, a few things to note. First is that only the vertical component of the momentum was affected. So only the vertical component of the momentum was affected. What this tells me is that initially the ball was moving up and to the right pretty quickly. And then in the final case, I should make this red, shouldn't I? There we go, to make it color-coded. Here's what PI looks like roughly. And in the end, PI was a little bit smaller, or PF. PF, the final momentum, was a little bit smaller. Its x component stayed the same. The force did not act to change the x component. It only changed the y component, the vertical component. So the change in momentum always points in the same direction as the force. So this is still 25 kilogram meters per second and 25 kilogram meters per second. Whoa, meters per second in the x direction. The only one that changed is the y direction. The y component, rather, of the momentum. Okay, another way to say that is on its way up, as this ball is arcing through the air, it starts out with a high speed, it starts out with a high momentum, and then gravity kind of eats away at that momentum. Okay. If I were to follow this all the way to the top of the arc, the ball's momentum is not 0, but the x or the vertical component, the y component, is 0. So the momentum for this ball as it arcs through the air will never be less than 25. It can't get rid of that x by gravity alone. It needs like friction or something, some kind of force that acts not only in the vertical direction. So the momentum of this ball is never 0, at least not until it like hits the ground and comes to a stop or whatever. Throughout this arc, the momentum is always non-zero, and in particular, it's always greater than the x component. So again, the reason it's always greater than the x component is because the y component is the only one that gets affected by gravity. So the y component can swing all the way down to 0. That's what we see at the top. It has no velocity in the vertical direction. It only has velocity in the horizontal direction. The other way I wanted to talk about this ball example was with the Earth and the ball as a combined system. So say I've got my Earth. Oop, hello. And I've got this dramatically pretty dramatic orbit actually for this baseball now, whatever ball it is. So I've got this ball that's being thrown. Here we go. Here's its initial momentum. So again, this is going to be reminiscent of the first video in this little series. What I want to pull your attention to here is that the change in momentum of this ball was a negative number, or a vector that points down in the vertical direction. So the change in momentum of the ball over that 2-second interval, here's delta p. Delta p for the ball points down. Delta p for the ball points down. Now, if I consider the entire Earth ball system, so everything that's interacting here is now contained inside my little system boundary. If I contain it all in one place, well, now all of the interactions, all of the forces between the members of the system are internal. So gravity, which acts on the ball from the Earth, is now like part of my system. So similarly, the ball attracts the Earth. So it turns out that the force is the same. That's Newton's third. So kind of like trying to tie that back to previous lectures. But the force that the Earth experiences is the same, which means that is 2 kilograms times g, so 20 newtons. So force, and I'll say force here, also 20 newtons. There we go, just to make it a little bit more graphical. So as this ball is falling back to the Earth over that 2-second interval, the momentum of the Earth is also changing by the same amount. So delta P Earth changes by the same magnitude and in the opposite direction. So as the Earth pulls the ball to the ground, the ball pulls the Earth toward it, I guess toward the sky, if you like. Okay. Obviously, that momentum change is very small, so let's just, for fun, let's see how much the momentum of the Earth changes, or the velocity of the Earth changes. So the Earth's momentum changes by a magnitude of 40 kilogram meters per second. That's mass times change in velocity for the Earth. This will be fun. Okay, now what's the mass of the Earth? And again, the 40 comes from the part above, where we solved for the change in, here we go, for the change in momentum of the ball. So they cancel each other out, so to speak. Total momentum is conserved. Okay, so 40 kilogram meters per second for the Earth as a subsystem. So real quick, I'm going to look up the mass of the Earth. I'll be right back. Okay, so it turns out the mass of the Earth is 5.97 times 10 to the 24th kilograms. 24 kilograms, which means that the change in velocity of the Earth corresponding to this interaction with this 2 kilogram ball over 2 seconds is 6.697 times 10 to the negative 24th meters per second, which, if I've done my math right, means that if you were to take this velocity, this change in velocity, if that was the only velocity the Earth had, it would take something like the lifetime of the universe to move 1/10 of a micron, which is 1 times 10 to the minus 7, sorry. 1 times 10 to the minus 7 meters, 1/10 of a micron. So pretty slow. But there is an effect. There is balance in the universe.